welcome to this problem walkthrough. Today, we'll be exploring problem number 2076, process restricted friend requests. In this session, we'll break down the challenges, examine the approaches, and walk step by step through the solution. Let's dive in. The problem involves a social network with n people, labeled from 0 to n1. You are given two arrays, restrictions and requests. In the restrictions array, each element, A_I, B_I, specifies that person A_I and person B_I cannot be friends. Meanwhile, the requests array contains friend requests, where U_J, V_J, represents a request for person U_J to become friends with person V_J. These requests are processed in order, and the goal is to determine if each request is valid. A valid friend request means that accepting it does not violate any restrictions. A violation occurs if the two people in the request either become direct friends or are indirectly connected through other people, forming the same connected component in the friend graph. The final output is a Boolean array result, where each entry indicates whether the corresponding request is valid or not. Here, we define the input and output of the problem. The input includes n, the number of people in the network, where 1 equals n equals 1000. The restrictions array contains unique pairs, A_I, B_I, specifying which pairs of people cannot be friends, with a maximum length of 1000. Similarly, the requests array contains unique pairs, U_J, V_J, representing friend requests, also with a maximum length of 1000. The output is a Boolean array result, where each element corresponds to whether a friend request is valid. For example, if there are two requests and result equals true, false, it means the first request is valid, but the second one is not. Let's consider a sample example to clarify. In example 1, we have n equals 3, restrictions equals 0, 1, and requests equals 0, 2, 2, 1. The output is true, false. Initially, no one is connected. For the first request, 0, 2, person 0 and person 2 are not restricted from being friends, so they become friends, forming the connected component 0, 2. The result for this request is true. For the second request, 2, 1, accepting it would create an indirect connection between person 0 and person 1, violating the restriction 0, 1. Therefore, this request is denied, and the result is false. This example illustrates how restrictions can apply not only to direct friendships but also to indirect connections within the network. In example 2, we again have n equals 3 and restrictions equals 0, 1, but the requests are 1, 2, and 0, 2. The output is true, false. For the first request, 1, 2, there is no restriction preventing person 1 and person 2 from becoming friends. They are connected, forming the component 1, 2, so the result for this request is true. For the second request, 0, 2, accepting it would indirectly connect person 0 and person 1, violating the restriction 0, 1. As a result, this request is denied, and the result is false. This highlights how the order of requests matters since the network evolves as friendships are processed. In example 3, we have n equals 5, restrictions equals 0, 1, 2, 3, and requests 0, 4, 1, 2, 3, 4. The output is true, true, true. For the first request, 0, 4, there is no restriction, so person 0 and person 4 become friends, forming the component 0, 4. The result is true. For the second request, 1, 2, there is also no restriction, so person 1 and person 2 become friends, creating the component 1, 2. The result is true. Finally, for the third request, 3, 4, person 3 and person 4 are not restricted and can form a connection. The network now has components 0, 4, 3, and 1, 2, and the result is true. This example shows that multiple connected components can exist in the graph. The problem comes with several constraints and edge cases to consider. First, the number of people, restrictions, and requests can be as large as 1000, so the solution must be efficient. If there are no restrictions, all requests are automatically valid. If there are no requests, the output is simply an empty array. Self-loops, where people request friendships with themselves, are not included in the problem. Additionally, the graph starts with all nodes disconnected, and the solution must properly handle forming multiple connected components. Finally, for large inputs, it's critical to ensure the solution can scale to handle the maximum constraints. These considerations will guide us in designing an optimal approach to solve the problem efficiently. To solve this problem, we first consider a brute force approach. The idea here is straightforward: process each friend request one by one and check if it violates any restriction. To do this, we can represent friendships as a graph or adjacency list and use graph traversal methods like DFS or BFS to determine if two restricted nodes, let's call them A_I and B_I, are connected through any path that includes the new friendship. While this method is simple to implement, it suffers from inefficiency. Checking restrictions for every single request means traversing the graph repeatedly, which can result in high computational costs as the number of people and restrictions grows. Specifically, the time complexity for this approach is O(r*(n), where R is the number of restrictions and N is the number of people. The space complexity is O(n), since that's what we need to store the graph. While this approach gives us a way to solve the problem, it's clear that it's not scalable for larger inputs. Now, an optimized alternative is the union-find approach, also known as the disjoint set union. This method is more efficient because it dynamically manages groups of friends. Initially, each person starts in their own group. As we process each friend request, we use the union-find structure to check if adding this friendship would violate any restriction. Specifically, for each restriction, A_I, B_I, we ensure that the two people involved are not part of the same group by using the find operation. If they are in different groups, we can safely merge their groups using the union operation. If they are in the same group, the request must be rejected. This approach is efficient because the union-find data structure allows us to perform these operations in nearly constant time, thanks to techniques like path compression. The time complexity for this approach is O(m*alpha n plus R, where m is the number of friend requests, alpha n is the inverse Ackermann function, which is nearly constant, and R is the number of restrictions. The space complexity remains O(n), as we only need to store the parent and rank arrays for the union-find structure. While there is also an alternative optimized graph-based approach, it's less efficient because checking connectivity dynamically using BFS or DFS is computationally more expensive than union-finds operations, leading to higher time and space complexity. The union-find approach is the strategy we chose for this problem because it offers the best balance of efficiency and simplicity. The key insight here is that restrictions are only violated if two restricted individuals belong to the same group. By using the union-find structure, we can focus solely on group leaders during our checks, which eliminates the need for exhaustive graph traversals. This makes the method not only faster but also easier to implement. Additionally, union-find handles dynamic connectivity checks and merges with near-constant time operations. Compared to the brute force approach, this method avoids redundant checks, saving significant computation time. Similarly, it outperforms graph-based approaches in terms of both space usage and operational speed. Ultimately, the union-find approach strikes the right balance between computational efficiency and implementation simplicity, making it the optimal solution for processing restricted friend requests in this problem. To solve this problem, we're essentially managing groups of friends while ensuring that certain restrictions are not violated. Think of each individual as a node in a graph. When a friend request is made, it's like drawing an edge between two nodes. However, the restriction list defines pairs of nodes that should never end up in the same connected component. This setup makes the union-find, or disjoint set union, DSU, data structure a natural fit for the problem, as it efficiently tracks connected components in a graph. To start, we initialize the union-find structure with two key components: the parent array, where each node initially points to itself, and the rank array, which helps optimize the merging process by keeping trees as shallow as possible. This setup will allow us to quickly and efficiently determine if two nodes belong to the same component, as well as merge components when necessary. Once the union-find structure is initialized, we begin processing the friend requests. For every request, UV, the first step is to ensure that it doesn't violate any restriction. This involves checking each restriction, X, Y, to see if X and Y are in the same component. If accepting the request would cause U and V to merge their components in a way that also merges X and Y, the request must be rejected. Otherwise, we use the union operation to merge U and V into the same component. To make these operations efficient, we apply two key optimizations to the union find structure. The first is path compression, which speeds up the find operation by flattening the tree structure whenever we access a node. The second is union by rank, where we always attach the smaller tree to the root of the larger tree, keeping the overall structure balanced. These optimizations ensure near constant time performance for each operation, even as the number of requests grows. The union find data structure is the backbone of our solution, with the parent and rank arrays enabling efficient management of connected components. While the adjacency list is not strictly necessary, it can be used for visualization or debugging purposes to represent the graph more explicitly. There are several edge cases to consider. For instance, if there are no restrictions, we can confidently accept all friend requests as no constraints exist. On the other hand, conflicting requests arise when accepting a request would directly violate a restriction, resulting in rejection. Cyclic friendships, where nodes form a cycle, are inherently handled by the union find structure, as it ensures connected components are well defined. To bring this all together, the pseudocode outlines the implementation of the union find class, starting with the initialization of the parent and rank arrays. The find function, enhanced with path compression, retrieves the root of a node's component, ensuring efficiency during repeated queries. The union operation, shown here, merges two components by attaching one root to another. Depending on the rank values, the smaller tree is always attached to the larger tree's root. If both trees have the same rank, we arbitrarily choose one root and increment its rank. With these operations defined, we can process the friend requests. For each request, we initialize a flag, can_accept, as true. We then iterate through the restriction list, checking if any restriction is violated by the potential merging of U and V. If a violation is detected, we set can_accept to false and skip the union operation. If no violations are found, we merge the components of U and V using the union operation, effectively accepting the request. This approach allows us to process each request sequentially while dynamically maintaining the connected components and adhering to the restrictions. Finally, after determining whether each request can be accepted, we append the result either true or false to the output list. This list is then returned as the final result, indicating the status of each request. The overall complexity of our approach is efficient, thanks to the optimizations in the union find structure. The find and union operations have an amortized time complexity of O, alpha, n, where alpha, n, is the inverse Ackermann function, which grows extremely slowly. When processing the requests, for each of our friend requests, we check up to m restrictions, making the total complexity O, r*m*alpha, n. This ensures that our algorithm remains scalable even with a large number of requests and restrictions, making it well suited for real-world scenarios with typical constraints. Here, we start by defining the class solution and implementing the friend requests method, which takes three parameters: n, the number of people; restrictions, a list of restricted friend pairs; and requests, a list of friend requests to process. Inside, we define two helper functions, find and union. The find function implements the path compression technique to efficiently find the root of a node in the union find structure. If the parent of a node is not itself, we recursively find its root and compress the path by updating the parent to point directly to the root. The union function merges two groups by connecting their roots. If the roots of the two nodes are different, we make one root the parent of the other, effectively merging the groups. Next, we initialize the union find data structure by setting up the parent list, where each person initially points to themselves as their own parent. We also create an empty list called result to store the outcome of each friend request. Then, for each friend request involving U and V, we temporarily find their roots using the find function. We set a flag can_b_friends to true, assuming they can be friends unless proven otherwise. Now, we check each restriction to ensure that forming a friendship between U and V does not violate any constraints. For each restriction pair, A, B, we find their respective roots using the find function. If the roots of U and V match the roots of the restricted pair, A, B, in either order, it means connecting U and V would violate the restriction. In such a case, we set can_b_friends to false and break out of the loop. If no restriction is violated and can_b_friends remains true, we proceed to unite the groups of U and V using the union function. This ensures that they are now part of the same connected group. Regardless of whether the friendship is allowed or not, we append the result of the current friend request to the result list. Finally, after processing all the requests, we return the result list, which contains a true or false for each request, indicating whether the friendship was approved or denied. This method efficiently handles the constraints and requests using the union-find data structure for optimal performance. Here, we start by setting up the union-find data structure, which is essential for efficiently managing connected components in this problem. The parent array is initialized so that each node points to itself, indicating that initially, each node is its own leader or representative. Next, we define the find function. This function is responsible for returning the leader of a given node, and it uses path compression to optimize the structure. Path compression ensures that during traversal, all nodes in the path directly point to the root, reducing the lookup time for future operations. Finally, we have the union function, which merges the groups of two nodes by linking their roots. If the roots of the two nodes are different, we set the root of one to point to the root of the other, effectively combining the two sets into one. Now, we create a list called result to store the outcome of each friend request. For every request, we extract the two users, U and V, and find their respective roots using the find function. We then assume the request can be granted by setting can-be-friends to true initially. To verify this assumption, we iterate through all the restrictions. For each restriction, we check if the two users involved in the request belong to restricted groups. If their roots match the roots of the restricted pair, we conclude that the request cannot be granted and set can-be-friends to false. If the request can be granted, we merge the groups of U and V using the union function. Finally, we add the result of the request, true or false, to the result list. The method concludes by returning the result list, which contains a Boolean value for each friend request, indicating whether it can be granted or not. This implementation ensures that we efficiently handle the friend requests while respecting the given restrictions, leveraging UnionFind for optimal performance in managing group connections. In this example, we start with 4 nodes and 2 restrictions, 0, 1, and 2, 3. The friend requests are 0, 2, 1, 3, and 0, 1. First, we initialize the UnionFind structure where each node is its own parent, represented as the array 0, 1, 2, 3. We also initialize an empty result list to store the outcomes of the requests. Now we process the first request, 0, 2. The roots of 0 and 2 are found to be distinct, 0 and 2 respectively. Since there are no restrictions that involve both 0 and 2, we can safely union these nodes. After performing the union operation, the parent array updates to 0, 1, 0, 3, and we append true to the result list, indicating the request was successful. Next, we handle the request 1, 3. The roots of 1 and 3 are distinct, 1 and 3. Since there are no restrictions that involve either 1 or 3, we can union these two nodes. After performing the union, the parent array updates to 0, 1, 0, 1, and we append true to the result list. Now we move to the request 0, 1. The roots of 0 and 1 are distinct, 0 and 1. However, this time, the restriction 0, 1 explicitly forbids these nodes from being connected. As a result, we do not perform the union, and we append false to the result list. The final output for this example is true, true, false. In this second example, we consider 5 nodes with restrictions 0, 4, and 2, 3. The friend requests are 0, 1, 3, 4, and 1, 4. We initialize the UnionFind structure with each node as its own parent, represented as 0, 1, 2, 3, 4, and an empty result list. For the first request, 0, 1, the roots of 0 and 1 are distinct, 0 and 1. Since no restrictions involve these nodes, we can safely union them. Performing the union updates the parent array to 0, 0, 2, 3, 4, and we append true to the result list, marking the request as successful. Next, we process the request 3, 4. The roots of 3 and 4 are distinct, 3 and 4. As there are no restrictions involving these nodes, we union them without any issues. The parent array updates to 0, 0, 2, 3, 3, and we append true to the result list. Now, for the request 1, 4, the roots of 1 and 4 are found to be 0 and 3, respectively. Here, the restriction 0, 4 prevents these nodes from being connected, as 0 belongs to the group containing 1, and 4 belongs to the group containing 3. Thus, we do not perform the union, and we append false to the result list. The final output for this example is true, true, false. In our third example, we have 3 nodes with restrictions 0, 1, and 1, 2. The friend requests are 0, 1, 1, 2, and 0, 2. We initialize the union find structure with each node as its own parent, 0, 1, 2, and an empty result list. For the first request, 0, 1, the roots of 0 and 1 are distinct, 0 and 1. However, the restriction 0, 1 prevents these nodes from being connected. As a result, we append false to the result list without performing any union. Next, we process the request 1, 2. The roots of 1 and 2 are distinct, 1 and 2. However, the restriction 1, 2 explicitly forbids these nodes from being connected. Therefore, we append false to the result list without performing a union. Finally, we handle the request 0, 2. The roots of 0 and 2 are distinct, 0 and 2. While there is no direct restriction between these nodes, the transitive restrictions 0, 1, and 1, 2 imply that 0 and 2 cannot be connected either. Thus, we append false to the result list. The final output for this example is false, false, false. To understand the time complexity of this solution, we start by analyzing the initialization step. Here, a parent list is created to represent each node in the union find structure, which takes n time because we initialize an entry for each of the n nodes. Next, we process each friend request, u, v, in the input list. The first operation for each request is the find operation, which determines the root parent of a node. Path compression ensures that the find operation is highly efficient, with an amortized time complexity of O, alpha, n, where alpha is the inverse Ackermann function that grows extremely slowly. Since we call find twice for each request, once for u and once for v, the cost per request for this step is O, alpha, n. This sets the foundation for analyzing the subsequent operations involved in handling friend requests and restrictions efficiently. Now, let's consider the restrictions check for each friend request. For every restriction, A, B, the algorithm uses the find operation to determine the root parents of A and B. This requires 2 calls to find for each restriction, resulting in a time complexity of 2m** O, alpha, n, for m restrictions. Since this check is repeated for all k friend requests, the combined cost for checking restrictions across all requests becomes O, k** m** alpha, n. If no restrictions are violated, the algorithm proceeds to perform the union operation for the nodes u and v. The union operation, like find, is also an almost constant time operation, with an amortized complexity of O, alpha, n. In the worst case, a union operation is performed for each of the k requests, contributing O, k** alpha, n, to the total complexity. When we combine all these steps, initialization, restriction checks, and union operations, the overall time complexity is dominated by the restrictions check, resulting in O, k** m** alpha, n. Here, k is the number of requests, m is the number of restrictions, n is the number of nodes, and alpha, n, is the inverse Ackermann function, which is practically constant for real-world input sizes. Next, let's analyze the space complexity of the solution. The union find data structure requires a parent list that stores 1 integer for each of the n nodes, which takes O, n, space. Additionally, the algorithm maintains a result list to store the outcome, true or false, for each of the k friend requests, contributing O, k, space. The recursion stack used by the find function also needs to be considered. With path compression, the height of the tree in the union find structure is logarithmic in the worst case, so the recursion depth adds O, log n, space. Finally, temporary variables like root_u and root_v require constant space, which is O, 1. Combining all these components, the total space complexity of the solution is O, n plus k, as the union find structure and result list dominate the memory usage. This makes the approach highly space efficient for large-scale inputs. Comparing this optimized approach with a naive solution highlights the efficiency of using union find. A naive approach would rely on simulating friend connections with adjacency lists or matrices and manually checking each pair of restrictions for every friend request. This would result in a time complexity of O, k m*n, where iterating through restrictions for each request is expensive. Additionally, maintaining an adjacency matrix would require O, n², space, which is impractical for large values of n. In contrast, the optimized approach leverages union find with path compression to reduce the time complexity to O, k m*alpha, n, where alpha, n, is effectively constant. The space complexity is also reduced to O, n plus k, as it avoids the need for large adjacency structures. This optimization makes the algorithm both time and space efficient, particularly for scenarios with a high number of nodes and requests. Analyzing the best, average, and worst-case scenarios helps us understand the behavior of the algorithm under different conditions. In the best case, all friend requests can be granted without any conflicts, meaning the algorithm only performs the find and union operations without extensive restriction checks. Here, the time complexity is O, k alpha, n. In an average case, some requests are rejected due to restrictions, and the algorithm needs to check a portion of the restrictions for each request. The time complexity in this scenario lies between O, k alpha, n, and O, k m alpha, n, depending on how many restrictions are evaluated. In the worst case, every restriction is checked for every friend request, and the majority of requests are rejected, leading to the maximum time complexity of O, k m alpha, n. This worst-case complexity is still efficient due to the near-constant time cost of union find operations. Finally, let's validate the time complexity with a mathematical proof. The union find operations, find and union, are optimized using path compression and union by rank, which ensure that their amortized time complexity is O, alpha, n. When processing the restrictions, the algorithm iterates through all m restrictions for each of the k requests, making this the dominant term in the overall complexity. As a result, the total time complexity is O, k m alpha, n, where alpha, n, grows slower than any logarithmic function and is effectively constant for practical purposes. In conclusion, the optimized solution is highly efficient, leveraging the power of union find to minimize redundant computations. Its low time and space complexity make it particularly well suited for competitive programming and large-scale inputs, ensuring scalability and performance in diverse scenarios. When working on this problem, there are several common mistakes that can trip you up. First, not accounting for edge cases and restrictions is a frequent oversight. For instance, if the restriction list is empty, the solution should always return true for all requests, but it's easy to miss this and introduce unnecessary complexity. Another edge case to watch for is self-friendship, when a friend request involves the same person, such as U equals V. Depending on the problem's requirements, this may require special handling. Next, be cautious about using inefficient brute force methods on large inputs. For example, processing each request individually without optimization can cause your solution to exceed time limits, especially when the number of nodes or requests is very large, like n equals 10⁵. Instead, more efficient approaches like union find or graph algorithms can help process requests in near constant time. Additionally, incorrect validation logic for restrictions is another pitfall. It's critical to ensure that bidirectional constraints are handled. If A cannot be friends with B, then both A-B and B-A need to be checked. Transitive restrictions can also be tricky, where indirect relationships, like A being restricted from C through B, need to be accounted for. Missing these can lead to incorrect results. Another common variation involves data structure choices. Using a nested list to track restrictions can quickly become inefficient, as lookups in such structures can take n² time. Instead, using a hash set or an adjacency list allows for much faster access, especially as the number of restrictions grows. Additionally, some candidates overcomplicate their solutions by jumping to advanced data structures or algorithms, such as segment trees or unnecessarily heavy graph algorithms, when simpler methods like union find or BFS/DFS are often sufficient. Keeping the solution as streamlined as possible without losing efficiency is usually the best approach. Now, let's discuss some valuable interview insights related to this problem. First and foremost, union find is a key technique to master. Many variations of this problem are best solved using union find, so being comfortable with its implementation, including path compression and union by rank, is essential. Another critical insight is to think about graph connections. At its core, this problem often involves analyzing connected components in a graph. Visualizing these connections can help identify patterns and clarify the solution. It's also important to consider trade-offs between time and space. While Union Find is highly efficient in terms of runtime, it does require additional space. Be prepared to discuss these trade-offs during an interview. Also, always clarify the restrictions with your interviewer to ensure you fully understand constraints like bidirectionality and transitivity. Misinterpreting these can lead to a flawed solution. Finally, make sure to explicitly test edge cases, such as scenarios with an empty restriction list, a single request, or a network where all friendships are restricted. These cases can often reveal underlying issues in your logic. This problem also shares similarities with several related problems that can help strengthen your understanding. For example, LeetCode 1319, which focuses on the number of operations needed to make a network connected, is heavily based on Union Find and analyzing connected components. LeetCode 839 explores similar concepts through the problem of finding connected components in a graph of similar string groups. LeetCode 990 involves validating constraints using Union Find, specifically for equations involving equality and inequality. Finally, LeetCode 1970 uses Union Find to analyze connectivity in a grid, offering yet another perspective on how this technique can be applied. Alongside these related problems, there are two main approaches you can use to solve this problem. The optimal method is Union Find, which has a time complexity of O, n plus m asterisk alpha, n, where alpha, n, is the inverse Ackermann function. This approach also has a space complexity of O, n, as it requires arrays for parent and rank. The trade-off here is the additional space needed to achieve efficient performance for large inputs. Alternatively, a graph-based validation using BFS or DFS can be used. This method has a time complexity of O, n plus m, with an adjacency list representation and similar space complexity. While simpler and more intuitive, it might be slower for dense graphs or require extra logic to handle restrictions properly. Finally, there is the brute force approach, which is the simplest to implement but not practical for large inputs. Its time complexity is O, m asterisk r, where m is the number of requests and r is the number of restrictions. It has a space complexity of O, 1, making it space efficient, but the inefficiency in handling large datasets is a major downside. This approach might be suitable for small-scale problems, but for competitive programming or real-world applications with high constraints, it's better to use optimized methods like Union Find or graph-based algorithms. Balancing simplicity and efficiency is key when choosing the right approach for this problem. Great job making it to the end. We summarized the problem, walked through the brute force approach, and discussed key takeaways. Remember, practice makes perfect, so keep solving more problems. Thanks for watching, and don't forget to like and subscribe for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!